Good morning. This is a webcast of how to compute complex eigenvalues by hand. Now you can actually compute these complex eigenvalues using the TI-89, or you can use Maple, and there are packages online that are free that will also compute the complex eigenvalues. And I'm going to talk about what they give you versus what you actually get by hand. So I'm going to start with a simple example, but before that I just want to remind you that when we have complex numbers and we multiply them, so if I have an a plus bi and I want to multiply it to a c plus di, I need to use FOIL. So I would actually multiply the first two, which would give me ac, multiply the outer two, which gives me a times d times I, and then the third term would be the inner two, bi times c. And then we have the last two, which gives you bdi squared. Now recall that I squared is really minus 1, so this bd that you have at the end, the I squared becomes minus 1, you have minus bd. I love to think of FOIL as Mr. Smiley. Do you see Mr. Smiley here? So we typically express this product by separating the real part with the imaginary part. So you see that I've grouped the AC minus BD together. That's the real part of the complex eigenvalue. And then I've put together the AD plus BC, which is the imaginary part. So I'm going to start off with a very simple example just to show you how to, and I'm going to walk you through this step by step. So the first step is to subtract lambda down the diagonal and take the determinant to find the eigenvalues. So when we do that, we get a very simple looking polynomial, lambda squared plus 1, and that when we set it equal to 0 and solve, we get lambda squared is minus 1, or lambda is plus or minus I. So it's probably it's the simplest complex eigenvalue you can think. The hard part of all this is finding the eigenvectors. So I'm going to give you the process for lambda equals I, the first eigenvalue, and I'm not going to do it for lambda equals minus I because the process is the same and everyone knows I hate doing these computations. So I'm going to be a minimalist and do only part of them. So you subtract the I down the diagonal, so you get this matrix right here, and you're row reducing this matrix, of course augmented, set equal to 0. When we do this, we get minus I 1 0 and minus 1 minus I 0. You'll notice that I'm going to be very careful, and I'm very careful for two reasons. The work with the complex eigenvalues is a little more complicated, and I make a lot of mistakes, so I have to be very careful when things get more complicated. So my goal is going to be to get rid of row 2. And I'm going to do that by observing that this 1 over here can be utilized by multiplying it by I and then adding it to the second row to cancel the minus I out below it. So I'm going to do that. I'm going to take row 1 and multiply through by I. Now minus I times I is really minus 1 times minus 1 because I squared is minus 1. So I get eventually a matrix at the end where I have 1 in the first component and I in the first row second component. And I did this without going to and adding row 2, which I usually do with non-complex eigenvalues or non-complex work. I just go and do row 1 plus row 2 or whatever I need to do as one swift move. I'm splitting this up. I'm doing the I times row 1 first, simplifying down the answer, and then I'm going to add it to row 2. So here we are, I just copied the previous computation. Now I will do row 1 plus row 2, which wipes out entirely row 2. And then the process is the same. I extract out what I have in row 1, and I solve for V1 in terms of V2, and I get this eigenvector. And this vector that you get is really in parametric form, but this isolated vector that you get is the basis for the eigenspace associated to I. Now in class what I did is I started playing with this answer, and there was a couple questions of why I was doing that. So realize that the eigenspace associated with this lambda is the entire span of that vector. The reason I played with that vector at the end is because Maple gave me a different basis vector. So sometimes Maple or the calculator, and my recollection is the calculator can give you some really crazy answers, but they can give you a different vector in the span as the basis. It doesn't necessarily have to be the one I found by hand. And that can be confusing to a student who's looking in the back of the book or Maple to check their work, because the answer that they get on Maple or the calculator looks so wildly different than what they found by hand. So let me give you an example. If I take any multiple of the basis that vector that I have, it is also a viable eigenvector. So for example, minus I times this vector gives me an entirely different looking vector, which you might look in the back of the book and say, oh, my answer is different than the answer that is in the back of the book or on Maple, but it really is not. It's really a scalar multiple of that eigenvector. Why we can't see that automatically is sometimes the scalar multiple is a complex multiple of whatever we had, like I just presented here. So it's sometimes difficult for us to eyeball the answer in the back of the book or on Maple and tell immediately that our answer is exactly the same as the answer that they're presenting. So that's why I had done that extra work, and keep that in mind when you're looking at the answer in Maple or the answer on your calculator or any online tool. So again, I want to remind you that you have to do the work all over again for lambda equals minus I, and you actually get a different eigenspace associated to this eigenvalue. So this work is not complete, but I'm done with it. I'm going to show you a more complicated example, but I'm going to do this more quickly, not breaking it down into steps. So here's a different matrix, and again, we find the eigenvalues first by finding the determinant of A minus lambda I, and set that equal to 0, and this is not as simple to solve, but we use the quadratic formula, and I've written the quadratic formula up there for you just to remind you what it looks like. So you put the coefficients right into the pockets of the quadratic formula and crank through, and notice that the way I simplify the numbers is probably not the way that you simplified numbers in high school or when you worked with complex numbers. You probably could have left it as 2 plus or minus a square root of minus 16 over 2, but notice I split them up. I almost do this autopilot because I'm trying to write that answer in terms of A plus or minus BI, where there's a real part and an imaginary part, and it's very clear what the real part is and it's very clear what the imaginary part is. And I recommend you always do this, because if you don't, you're going to have some grief associated with it as you go. Now we're going to find the eigenvector associated to the first eigenvalue, and as before, I'm not going to do the process again for the second eigenvalue because it's all the same work. So as before, we subtract lambda down the diagonal, so I get this matrix right here, and as before, I'm going to use the constant in row 2, which is minus 2, and try to utilize it to kill out the element that's right below it. So the constant I'm talking about is this minus 2. I observe that if I multiply that minus 2 by the negative of 1 plus I will get a negative multiple of what's right down below it, the minus 2i, and then if I add the row 1 to row 2, that term would drop out. So I have to think a little bit further ahead than I used to think with the just scalars that are just real numbers and not complex. So I'm going through the process. I'm going to go through it a little bit more slowly than I did before, because now I have to do a Mr. Smiley in my calculations. So here we have the first move is to multiply by the negative of 1 plus I, which I have now transferred as minus 1 minus I, to row 1. So I go through that. And notice that this first term up at the top that I've circled requires me to do some work. And I have to be careful, especially with what you know about me and minus signs. And in fact, I'm going to tell you a little secret. I actually made a mistake as I did this, and I realized I made a mistake because I realized eventually that I'm not going to get a row of zeros on the bottom, which I need to get, otherwise I won't have an eigenvector. Eigenvectors cannot be 0. So that was the mistake I made. I took the 2 times I squared and I had it as minus 4. When it's not minus 4, it's actually 2 times minus 1, which is minus 2. So I corrected that. and I realized that I get minus 2 minus 2, which is minus 4 there. So popping that in, now that it is broadcast on YouTube, everybody will know about my mistake-making secrets. Here we are at minus 4, 2 plus 2i on the first row, which turns out to be the negative of what's right below it. So now I can add row 1 to row 2. I get the row of zeros below. And as before, it's just a little bit more messy. I go through the process of solving one component in terms of the other, and then setting that equal to in parametric form, and then I get the eigenspace. Now here you have a more complicated looking span, and as you can imagine, you know, you can get some really crazy things for other multiples. So for example, square root of 3 times this eigenvector in the basis is also a viable eigenvector. And sometimes the calculator will give you something like that, and you're wondering where in the world did they get this from. They have a method of finding the eigenvectors that is a different process than yours. It gives you a different eigenvector in the span than what you came up with, and that's all you have to really know. So I'm going to stop there. Send me questions if you have any.